Thank you first to Andrea for doing such an awesome job of putting together this workshop and meeting, and really appreciate the opportunity to be here. I've learned a lot over the last few days. I appreciate the fact that you guys all came. Sorry the fact that you had to cut short whatever you were doing, but thank you for being here. I want to talk about 2 or 3 things, and I'll start by maybe highlighting these, because they're probably I'll get to at the end, and maybe I'll be in a hurry and I won't talk as much about them as I do about the first part, the friction law stuff. But it's true that we have been able to recently see changes in elastic wave speed and elastic properties of the fault zone prior to failure for a whole range of modes. And part of what's interesting about it to me is the fact that you see it for slow slip and for intermediate velocities of the stick slip velocity and for dynamic rupture in the lab. So I think it gives some hope that there's a common mechanism that could be explored in the field. So the other part of it that's here is about using machine learning to predict laboratory earthquakes using acoustic emissions that are recorded from the fault zone. Very interesting new stuff that I've been involved in. In fact, this is the first paper that was written on it. I'm not an author on, but I want to bring a few things out of it, because we've used machine learning to predict some things about the whole range from fast to slow laboratory stick slip events. And again, it connects in with, so the overall idea that I'd like to talk about is this friction law. Let's say Radin state can ask the question, to what extent can it describe what we see in the lab? And I'll start by doing that. Okay, and hopefully by now you've appreciated the fact that lots of places helped us do this, funding-wise, and lots of people were involved, and I will introduce some more of these people as we go along. Okay, now the spectrum of fault slip behavior is exactly what is meant by that. For me, it is all of these things. And if we start at the bottom, slow stuff, aseismic slip, creep, fault creep, and slow precursor, a lot of names for things that involve faults moving faster and faster, and at some point starting to radiate elastic energy when there's a slip event. First, dominantly at low frequencies, and then at high frequencies, and eventually ordinary earthquakes. Okay, so I've arranged these things from bottom to top, and I will, and I think a lot of people kind of use slow earthquakes to mean all of those things in between. And of course, not precisely, but basically, slow earthquakes for me means all those things in between. And then, just to be clear, this is a plot of the Pacific Northwest in the US and Canada, showing the locations of tremor events on the subduction zone as a function of time, and you have to pay attention to this is written in the confusing way that Americans write dates of December 4th in 2015 to March 4th in 2016. 3 months worth of data, and you see the propagation of these events along the interface. So there's something going on that's happening very slow, not dictated by elastodynamics, and that is the point of where we've been trying to go. Okay, ordinary earthquakes, everybody knows all about them. Radiation, damage. Slow earthquakes, a lot of people know about the slow slip, at least. Right, this famous place on the Hayward Fault. This is the University of California at Berkeley. Their stadium is built on the Hayward Fault, and it undergoes creep continuously. It's the side of it. But the question I want to ask is, why are they slow? Like, what sets that rupture speed? And I didn't spend a lot more time talking about it, but I want to make sure it's clear in your mind that this is not just a driven creep event. It's not just a relaxation. These events are quasi-dynamic in the sense that the stress that's relieved in the slip patch is showing up at the rupture front and driving the rupture. Just like, in a sense, we think of fracture mechanics. Same kinds of things are happening, except for the propagation velocity is not dictated by elastic wave speeds. I could almost say it has nothing to do with elastic wave speeds, because we're talking about things that propagate at meters per year, meters per day, nothing like meters per second. And you can see that this is a nice little picture that was made of Heidi Houston's data showing the propagation along the subduction interface here of these slow slip events. Okay, and just to be clear, like So this is 8th of August in 2010 to the 9th of September in 2010. You can see this rupture moves along here like a bilateral rupture. It just goes at a speed that doesn't make any sense relative to typical elastodynamics. Okay, so this is the motivation. Why are they slow? Is there a friction law that can describe this? Is there some viscous process that we should be thinking of? And then maybe more specifically, simply is just like, can this be described by rate and state friction? Sort of the backdrop for what I want to talk about. All right, we could start simple. You say, all right, we remember, how impressed we've all been by Brace and Byerly in 1966. It sort of says, stick slip, frictional stick slip could be a mechanism for earthquakes, and and there's some idea that the elastic hypothesis rebound makes sense. Fine. So if we take that view and then look carefully at a simple model for it, we've known for a long time that you can take a simple model like this and produce the sort of two end members of what goes on. In fact, even 10 years ago, 15 years ago, to some extent now, people think that, maybe it's not just end members. Maybe these are the only two things that happen. You either get stick slip or you get stable sliding, and there's kind of nothing in between. And I think that's not quite right, but that's one interpretation. So if I just put the rate and state friction law up here, and fortunately for me, I did a beautiful job of introducing everything about it this morning, I can start to ask questions about how the instability works, and I can say, if I write down frictional strength is a function of velocity and state, it looks like this. So that is the idea of rate and state, and then I can write down an evolution law, and I'll show a few more things about this in a minute. I can couple it to some statement about the elastic coupling, and these people came up with a nice little analytic solution that says this is a critical value of this stiffness. It's a stiffness because it has units of stress per displacement. There's a critical value, and basically what's important to realize about that critical value, and I just focus on this part of it, because in fact for slow events this part of it certainly doesn't matter. That part, the mass right there, is the lumped mass of the spring block model, and velocity and the other terms that are there. This will be important once inertia becomes important, but it won't be important at the nucleation stage, or the stage where a rupture is moving at maybe 10 kilometers per week. So if you look carefully at all this nice work that was done in the early 80s, and you look at this, okay, so here is just a visual description of this is friction, this is a perturbation in velocity, this is the evolution distance, the critical slip distance d sub c, and this is the new value. This is showing the velocity weakening case, v1 bigger than v0. And there's lots of details that you could talk about rate and state friction, and in fact I could motivate this without rate and state friction, but specifically want to talk about that today. The key point is that there needs to be some kind of frictional weakening that's fast relative to the rate at which elastic stresses can be relieved. And the rate that's important here is not a derivative with time. It is the change in strength per displacement, right? And so you can see it there. And I say, so this is the specific formulation for rate and state. We could do this in terms of slip weakening. And then just to say a couple more things about rate and state. Here are the terms. I think I did a really nice job this morning explaining maybe everything. I don't know if I need to explain anything more from that. If you've not looked a lot at rate and state stuff, maybe you thought, maybe this part of it, the steady state part of it is clear. But it does a lot more than that. It's capable of handling, in this case here, these are little experiments where you do a slide and wait and slide experiment to look at how fast aging occurs, how fast the frictional surfaces increase their strength with time. And okay, there's a bunch of details here, but then there's something very obvious, and that is that if you drive along at 3 microns per second when you're pushing, and you wait for 100 seconds, well then you produce that amount of aging, that amount of increase, and if you want to use old terms, static friction. But if you drive along at 1 micron per second and wait for 100 seconds, you see something pretty different, right? Qualitatively the same, quantitatively different. And rate and state describes all of that kind of together in an interesting way. So this term is very important. I'll keep coming back to it, but I said that there's a rate of weakening, and it's the weakening with respect to displacement. Okay, now, I not did 100% of a fabulous job this morning, but she left out one of my favorite things, so I have to put it in. And it is about this paper that was written by Ernest Rabinowitz in 1951. And he asked this interesting question just in his title, because he realized that if you have a static friction and a kinetic friction or dynamic friction, it's impossible for a physical system to change from one value to another instantaneously. Something must happen. The surface has to change. There needs to be some strain or displacement. Something has to happen. And he put this cool way together to measure it using this. And he put a model together because he had an idea that, well, at the contact junctions, right, the asperities of Bowden and Tabor, if they're sitting there for a while, and this is the contact, and as they move, well, the contact that did exist is eventually erased, right? And so by those pictures, in his 1951 paper, and they're almost exactly from it, he introduced this idea. He said, well, the real area of contact here is going to increase with log time. He's put the log in there. And that means that I can define a contact lifetime. And this is what I not defined this morning. So this becomes a very important part of the whole thing, is that if you simply have frictional aging by itself and nothing else, you'll always get velocity weakening. Because the faster you go, the shorter the contact time is, age is, and then the weaker the whole thing gets because the contact area is smaller. Now, obviously, things are more complicated than that, but there's at least that, okay? So he introduces this contact lifetime, and then introduces the idea that the critical slip distance is probably related to the size of these contacts. Right, now I'm not going to go through too many more details of the Radin state laws. I want to ask questions like this. But I should have said this already. I am happy to be interrupted now or at any other time. So if you've got a comment or a question or just a complaint, I'd be happy to hear it right now. Okay, so I want to talk about can we describe slow slip this way? And you can almost see right here that the answer is no. Well, in fact, it's no exactly if life is only this complicated. Because what these papers show, using a perturbation analysis, is that there is a hot bifurcation between these two states right here for, depending upon the details of this. Actually, for this particular law, there's not, and for the other evolution law that's commonly used, there is. That means that no matter what the size of the perturbation and velocity you put in, as soon as you're back and forth across this line, you'll either have stable or unstable sliding, and you won't get anything else. In fact, the only kind of unstable sliding you'll get is fast. You won't get slow. So, I don't know, maybe I could stop the talk right there and say it doesn't work, but in fact, the experiments show that something else goes on. And it's probably worth also pointing out that this numerical paper that was done in 1984 said, well, if you use a two-state variable law, so something a little bit more complicated, then there's a region of so-called permanently sustained oscillations in here. And they never studied, they didn't look at the velocity, the slip velocity of any of these things, but they showed a bunch of complicated behaviors, which I've just characterized here like this. And I'm going to come back to this plot, so I want you to see it now. So I have some elastic loading stiffness and some critical stiffness, which is the rate of weakening, the rheologic parameter. And depending upon where I am in here, I'm either going to get stable or unstable sliding, or this kind of quasi-dynamic region. And that becomes very important. Okay, so now for some experiments. And I hope you got to meet Paul Silver, and he was a fabulous guy. And I always remember being at meetings with him for quite a while, where he would say, how come you guys don't study slow slip? I was like, Paul, it's impossible. It doesn't happen in the lab. Can't make it happen. And part of the reason I have this slide in here is to say that, in fact, quite a few people have produced slow slip. In fact, people in this room. Yeah. What a lot of those studies that produce slow slip didn't really have were all the knobs and bells and whistles that allowed you to produce a lot of them, repetitive slow slip under kind of controlled conditions. So there are quite a few examples in the literature before we came into the picture of slow slip experiments that I think demonstrate a lot of things, but maybe not, I don't know. So the rest of this talk, obviously, is my perspective, okay? So I spent a lot of time trying to bring in all the old stuff, but there are, in fact, few examples of repetitive slow stick slip. But, okay, as of a few years ago there were. So now I want to show you some data and step through a few things to show you what happens in the experiment and also how it can be interpreted. This is just the shear stress divided by the constant normal stress in these experiments. It's double direct shear. No details. I'm happy to talk about them, but I don't think they matter. You drive up, there's a peak, you start to slide, nothing's sort of boring. And then just over a few hundreds of microns, you transition from stable sliding into this limit cycle of, these are all stick slip events. And you can see them grow, and they're approximately constant, not really. I'm going to show you something from there in a second. I guess I could just show you right now. And then I want you to pay attention to the fact that this and this are real effects. They are places where we stopped for a few minutes, the surfaces aged, and then when we started to drive again, the surfaces were stronger. So those are not weird artifacts or anything else. There's something that happened in the experiment, and they're a real effect, and you can see how quickly it goes away. After 1 or 2 cycles, the effect of that aging is gone. So if we look in detail at these things, I guess the main thing I want you to see is that we have, high precision data on what the stress drop is and also what the acceleration is. That's one view of it. If I show you sort of one slightly different view of an experiment just like that one, every one of these stick slip events, we can look at it and see there's some elastic loading period, then some kind of inelastic period, and then it fails. And we can see the full acceleration history of the event, right? We can in fact see that probably at least these events should not really be called stick slip. They're more like creep slip, because you can see in the background here, this is not really stationary. And so there's a range of things that happen, very much like in the talks that we heard this morning. Okay, so now if I show you, I'm going to show you a range of things to kind of develop where this comes from and then interpret it in terms of a theory. But if I'd use a range of normal stresses for the rest of the conditions the same, I see a range of behaviors. This is the normal stress on the surface. And these particular experiments are from a quartz powder, very fine grained powder. Everything is less than a micron or so. The contact area is just a few centimeters by a few centimeters. And we servo control the normal stress constant. There's a lot of control in these experiments, and there's a lot of reproducibility, but then there's also the usual thing with a real data set. But if I grab a few of those right here, and then align them up at 0 on the maximum in friction, and I just show the normalized values here so I can compare them, you can see that at 14 MPa, this is a pretty good stick slip event. These are the kinds of things that Paul Silver knew about, that Brace and Byerly talked about. Not quite. Brace and Byerly's stick slip events were much faster than this probably. They were probably over in 5 milliseconds or something like that. But look at how slow this one here takes almost a full second for the stress to drop. And then if you look at that slow one here, friction is a function of time and velocity, you see that the peak velocity is 80 microns per second. That's actually pretty slow, but you can see the whole acceleration and deceleration history associated with the stress drop, and that's kind of interesting. In fact, if you look as a function of normal stress, you can see a range of things. This is a suite of experiments that I want you to see some details in, and then I'll show you an interpretation of them. I don't know, maybe to start out you realize, okay, so Coulomb would have told us this in the 1700s, that if you just look at the shear stress at which something happens for a material as a function of normal stress, the higher the normal stress, the higher the shear stress. It goes up kind of linearly. And then the rest of this is more complicated. These are slow slip events down here, and you can see this transition between stable sliding and unstable, either fast or slow, is a function of displacement, and not perfectly linear, but let's say, happens faster at higher normal stress. If you look at the details of these things, and I'm making a shortened version of this, we did these experiments, a combination of them at Penn State and also in Rome at the INGV lab of Cristiano Colatini. And again, you see a range of behaviors here. The machine's different, the sample size is different, and so the transition occurs at a different normal stress. And I'll come to that in a second. But you see here that at 13, 13 and a half is basically just stable sliding. Then you get these complex unstable events, and these are all slow. long period modulation of the stick slip amplitude. That's kind of interesting. See an interesting thing here with small and large period doubling events, and you see this kind of continuous variation as a function of stress drop and duration of the events, or peak slip velocity. So that's one compilation of data, and then here's another. And basically, some details here you can see, and maybe I want you to see, but the main thing I want you to see here is that there's a spectrum of slip velocities during these stick slip events. Creep slip and stick slip events. Slow events down here, that's 60 microns per second at the peak velocity. This is kind of one experiment and the range of things that happened in that experiment as a function of strain. And then there's a bunch of experiments, you go faster and faster. Now, these are not, in fact, very fast stick slip events. They only get going at 4 millimeters per second, which is pretty slow. But we really cared about the slow part of it. If you keep going up here in normal stress, you'll get faster and faster, but they're already audible somewhere in here. This is being audible to somebody, audible even to my ears at my age. Okay, so these are like, I'm going to say, slow earthquakes in nature. These are like ordinary fast earthquakes in nature, in a sense. But first of all, I guess I want to make sure I understand and interpret the lab data, so you don't have to believe me that they are. In fact, maybe they're not. But what certainly happens in the lab is we have this range from fast to slow. And we could ask the question of, like, can we describe that with rate and state friction? Well, we already knew, these guys already showed us that if we simply have one state variable, that means one value of this state here and one critical slip distance that goes along with it, it doesn't work. You can't describe it, in fact. You can't even describe it if you use a more complicated elastic interaction. It doesn't work. But it turns out you don't have to add a whole lot to make it happen. So looking back at the data, I'd like to say, well, can we reproduce the range of stick slip rates that we see in the lab? And can we understand the displacement dependence of the transition from stable sliding to unstable? So I'd like to at least be able to explain those two things, like why this happens faster and then why these events are faster than these as a starting point. Okay. So, okay, the simple theory tells us we need to know K and K sub C, right? Because K sub C tells us about the weakening rate. K is something that we could play around with, and so let's go ahead and measure those. And this is one way that John Lehman did it. He did load-unload cycles, and he took the slope of this line in that region right there, and that's what's shown at these gray points here. And so this slightly funny maybe way of thinking about stiffness, but if you live in the friction world and you want to normalize everything, so we've normalized the stiffness too. So instead of a shear strength change per displacement, it is the shear strength change divided by the normal stress per displacement. Okay, so it has units of nothing per micron, or in this case, or millimeter. So we can measure the stiffness changes here as a function of displacement, just in general. And then we can measure them from every one of these stick slip events as well. And that's kind of partially what's shown here in these black events, black circles. So basically they're the same, and I'll put some numbers on there just because we are going to look quantitatively at these numbers. These are the exact numbers that we know work for this experiment, and we can do this experiment in a way that we can measure K sub C too. So we have 4.5, if you want, at 10 MPa, 4.5 megapascals per millimeter. And the reason I care about this displacement is because I really do want to see the difference between the higher normal stress experiments that transition into instability faster at smaller displacement than the other things. And so I can clearly see that there's a displacement dependence to my stiffness. Now I'm going to simplify this, so I'll go back if you want me to, but basically this is what it looks like. Right? And part of the reason for me to simplify this is because, if you're following carefully, you're nervous. Because this is going the wrong way. Right? If stiffness increases as a function of displacement, then no matter where we are, we should go toward being more stable, not more unstable. If we're anywhere near the stability boundary, that should make us stable. And I'm showing stiffness in this slightly funny way here because I want to include the possibility that there's negative values once I include K sub C, right? So K has got to be positive. But K sub C could be negative or positive depending upon whether or not I had velocity weakening or velocity strengthening. Now, I don't know, fortunately, we know how to measure K sub C. We've done it for a long time. In fact, everyone, including us, already knew what was going to happen as a function of displacement. It's been well known for a while that a lot of materials start out velocity strengthening and transition to velocity weakening with displacement associated with various things. These are from these exact experiments. This decrease in d sub c as a function of displacement is also sort of well known as a localization effect. So, okay, so there's a range of things that happen. I'm going to report k sub c from these exact values. And I'm just going to put those two things in a sense together exactly, right? So k sub c starts out like this. This is schematic. These numbers are not, right? This is exactly what k sub c ends up as, to the extent that it really looks like this blue line. There's scatter. It is 7 times 10 to the minus 4 per micron, and k is about 4.5 times 10 to the minus 4 per micron. Now the actual values don't matter because they involve in part the experimental apparatus for this. This blue line should be a function of the material, and so it does matter. Pay attention to the crossover here. That crossover right there is the place where it should be unstable. Everything before that should be stable, everything after that should be unstable, and in fact it is exactly that way, right? This already explains exactly what we see. Because as you make normal stress bigger and bigger, you move, the way I've normalized things here, you move that red curve down more and more. The blue curve is independent of normal stress if you believe the idea that neither b minus a or d sub c is a function of normal stress over this range. And I can almost guarantee you that it doesn't for lots of materials, but I can definitely guarantee you that it doesn't change much for this material because we looked at it. So here's another way, I think more convincing, exact same material we used in these experiments in Rome and also at Penn State. Here is a plot of this normalized value of k as a function of shear strain, and you see the way it increases. So the gray curve is k is a function of strain. And then the two red curves are for this experiment and for another higher stress experiment. Remember I said, because the way we're normalizing k with normal stress, it gets smaller and smaller. So the transition is predicted by this to happen earlier at higher normal stress, exactly like the way you see. Okay, so now let's say, what do we think we know? Well, in the lab, we know radiant state friction describes a bunch of other things about our experiments. And now I'm showing you that our experiments are well described by some aspect of this theory of the instability, right? The simple theory says that when k is less than k sub c, this rate of weakening, it'll be potentially unstable. And that's consistent with our data. What's not very consistent with our data at this stage is like a numerical model that says, oh yeah, I see the same thing. Because the numerical model shows that you either get a bifurcation, only stable and unstable, or that you get this, but it doesn't say anything about how fast these are. So I want to play around with that for a second. And I will ask the question of how I'm doing on time. I guess I'm doing all right. I didn't give you an outline, but I want to give you one now. And I've said all those things already. I want to talk a little bit about the mechanism for why they're slow in the lab. And I'm going to do that in the context of asking this question of, can I make this happen with numerical models? And then, with whatever time I have left, I'm going to talk about those two things. Okay. Well, now, of course, I didn't show you all of our data all at once. But it turns out that when you look at the relationship between friction drop and slip velocity, now I showed you a bunch of curves. Actually, so far, I only showed you things at one slip velocity. But if you change slip velocity at a given normal stress, so each of these curves are for a given normal stress. This is 7 MPa, 9, and 12. The faster you go, the smaller the friction drop gets at a given normal stress. And that is not predicted by slip weakening law. To model that, you have to have something that includes aging of the contacts. Otherwise, you'll never get that. So, okay, radiant state friction could predict one of these lines, but it doesn't easily predict that there's a normal stress effect of them. And another way to say that is to look at a given experiment and say, well, what happens if I just change the velocity when I'm right near the stability boundary? And this is what happens. And this is ugly looking data in a sense because it's real data, but it shows very clearly that when you go slow, you see a much bigger stress drop than when you go fast. and intermediate is in between, okay? And so what that is saying is that our simple theory says that the rate of weakening here is independent of anything, right? The K sub C is not a function of anything in terms of the way the simple version of this works. So the simple version of this, if we plot stiffness as a function of velocity, is just a straight line. If I go to high stiffness, I get stable sliding. When I fall below some threshold value indicated by K sub C, I can make instability happen. But what these data show you is that it actually looks like this. And this is K sub C has to be a function of velocity in some way like this. So let's look at that a little bit and make sure we believe it a little more clearly than what I showed you before. And John Lehman was fabulous at this stuff because there's a lot of weird coupling in these experiments, like displacement matters, net shear strain matters, because the sample develops a fabric, you get breaking of grains. So John ran in to each of the values in this table under the exact same conditions, and then produced this. So run into this displacement, and then go to 3 microns per second at 5 MPa. Make another experiment, do this. Every one of these is a separate experiment. And you clearly see basically what we saw before. That is for 7 MPa is maybe the easiest thing to look at, is that when you go fast, it's basically stable, like you're near that phase transition, if you will. When you go fast, you become stable. When you go slow, you become more unstable. And the farther you fall below this, the bigger the stick slip events get. All right, so now you can say, well, what do we have to do to rate state friction in order to reproduce that? And here's the answer. And it's slightly complicated looking. And the next slide I have will explain it, but it's even more complicated looking. So let's just look at this together for a minute. This is normal stress and velocity. So it is basically just points like what I just showed you, driving into different places in parameter space and then seeing what happens. And so all of these things are stable down here. And then the size of the stress drop, the unstable stress drop, is colored. I don't know. And there's, it's not a clear transition. It's just roughly a clear transition because these are tiny values, right? So at some point you have to say, well, is it really a friction drop or not? The point is that the higher the normal stress, the bigger the friction drop at a given velocity. And in fact, if you look at this relationship for K sub C, you rearrange it for normal stress, and then you ask the question of whether just D sub C, so the way I've written this right here, imagine that D sub C increases with velocity. We have some other data that show that, so we kind of guessed that'd be a good place to start. Well, that's what that solid line shows. I'm sorry, that's what this line shows. The solid line is just a guess about where it is. And that dashed line right there shows how this stability transition works if D sub C is a function of velocity. When you go faster, D sub C is bigger. So it's like as if, one interpretation is that the zone is wider over which slip is occurring. Actually works pretty well. Still just the experimental data, kind of unsatisfying. And it turns out that if you do a little bit of work in terms of the numerical model, and KJ Eam did that work, if you go back up and look at the result out of the Rice and Marina papers in 83 and other things, and they did part of this in those papers, but they didn't run the numerical models for them. And I could take you through all of this, but basically you have to say, well, what did I start out with? K sub C is this. It is the derivative of the steady state shear strength with velocity, which is what B minus A is. And then it is these other terms over here, these inertial terms that are here. And so if I go through and ask the question of how does, if D sub C is a function of velocity, or if individually A and B are a function of velocity, what does that do? Well, this numerical model solves that and comes up with a solution. And again, I don't really want to go through all the details of it, but suffice it to say that if I plot things in terms of normal stress velocity space, which is where I was living in my experiments, I have an analytic solution for that that looks like this. And then I have numerical models, and KJ loved to run numerical models and did all of those and color-coded them with velocity of the stick slip event that happened. Everything down here is stable as predicted, and then everything up here is going faster and faster at higher normal stress. This is 100 millimeters per second in the model. And then he put some fiducial lines on here to show where 10 millimeters per second was, or 1 millimeter per second was. And then these are interesting to look at because in part, especially this one was, for me, non-intuitive. This right here says, well, if d sub c increases with velocity like this, so this is velocity down here, and that is a plot of d sub c as a function of velocity. So you can see it's just linear with log velocity, which is something that we thought we knew before, but okay, this is now a numerical model. Well, you can see what it does is it expands the stable region, and it changes the velocities in a way that's not surprising. This is what was surprising a little bit to me, because a lot of people have already seen that if you have a transition from velocity strengthening to velocity weakening, you might be able to, velocity weakening to velocity strengthening, you might be able to produce the kind of instability that starts, and as soon as acceleration happens up to some velocity, you just lose the instability, it becomes stable. What KJ found is that you don't need to actually, you start with velocity weakening, b is bigger than a, and you don't ever get to velocity strengthening. And you still can have a situation where you have a slowdown of the events, right? You can produce unstable events in here, of course you can, but you can also produce a wide range of slow events in here. And you never got to the point where you were really velocity strengthening, just by having a reduction in the driving force, which is what b minus a is. All right, well, I feel maybe like I'm going to be okay spending another 5 minutes. I don't know. You remember now, I told you you could question, comment, or complain. So complain if you want to talk about time. But I want to show you at least one more thing relative to this, and so much of it is the same that maybe I don't need a lot. I only have five or six slides. Experiments of very similar configuration, but now we're going to shoot elastic waves through at 500 kilohertz. And we're going to ask the question of, are there changes in those properties in advance of any of the stick slip events? And in fact, there are. So here is shear stress. This is at a given normal stress, one of the experiments I showed you before. Shear strain, so it shows this transition from kind of like stable sliding to unstable events. And then right there, I've blown up some data. There's a half a second right there. And I've shown you the wave forms that are recorded by the PZTs from one side to the other. And they're shown here in this kind of plot that people like in this business, where this is time, right? So this is the wave trace. This is in microseconds. It takes something like 35 microseconds, 33 microseconds for the elastic wave to go through. And then plotted right on top of this is the shear stress curve. So you can see what happens, during there's the instability, right? And then shown right here is the flight time recovered by doing some really careful work in terms of cross-correlation of the events, right? So looking at the differences between these arrival times, you can see this. And this is useful to keep track of. This is 0.02 microseconds. That's the scale bar. So there's a lot of uncertainty in the way they measure these things, but, and that's the scatter you see, but you basically see a very clear change in the flight time as a function of the approach to unstable event. Now, if I turn that flight time, of course, we know the rest of the things about our experiment, so we can turn that flight time into a velocity. And if you do that, and now I'm showing you, some stick slip events, some slow ones and some faster ones. The velocities are down here. So, 50 to 100, these are fairly slow. These are faster. And they show very similar results. I'm focusing on this in a second, but just give you a chance to see that. That's 1% change in the p-wave velocity. P-wave velocity goes up initially when it's loading, then it stabilizes, and then it goes down, and then it drops during the unstable event. Okay? So now, if I focus on two of those, here's a slow one, here's a fast one, zoomed way in so that we can see what happens in detail with the change in p-wave speed. This is 20 meter per second scale bar. Right? And these things are going through it a kilometer per second. Then what you see, very clearly is that this drops off, stabilizes, and then starts to drop before the coseismic phase, which here is defined simply as the point at which the velocity of the slip velocity moves appreciably away from zero. So I guess the main thing I want to see is that, so for this whole range of slow to fast, you can easily see this precursory change in the wave speed, which is certainly associated with motion on the contacts of these particles. And in fact, if you then make a connection to what's been observed in the field, the times are off. The amplitudes of the velocity change, the magnitude of the velocity changes are off. They're not the same. But the sign is the same. This is what you see. This is what New et al. Saw, and Paul Silver was part of this in 2008. They happened to see a magnitude 3, and this is the delay time. And I don't know why they plotted it in this weird way, but it's fine with me. But just pay attention to the fact that the delay time is increasing this way, down, not up. So the velocity started to decrease before the magnitude 3 event, and then decrease, and then shows this time-dependent recovery. Right, so this time-dependent recovery has been observed many times in nature. That the wave speed decreases, and it's not surprising in a way. Like the fault slips, and so the contacts are all rejuvenated, and maybe you make a whole bunch of cracks in it. The wave speed goes down. Nobody's surprised by that. And then it recovers. Maybe people, so the recovery is showing you something about frictional aging. And so I just want to say that, so we're seeing very, very similar things in our experiments. And there's no break from slow to fast. It indicates that, whatever the mechanism is that makes it slow or fast is not fundamentally different in our experiments. Okay, now I only have about 4 or 5 more slides, and I probably have done everything I really want to do with this anyway. Let me just show you a couple plots here. These are stick slip events, and then predictions of them that are made using the acoustic emissions that come from the fault zone. And what exactly do I mean by that? Well, this is zooming in here. We've got PZTs all over the place right next to the fault zone. And this is a stick slip experiment like I've been showing you. And then it turns out that if you look at this is a blow up of what's important, but this is the crux of what goes on. Here's a stick slip event. There's another one. And here is the acoustic energy converted to strain that's been recorded. And basically, you look at that and you think, yeah, it's just noise. Especially if you look in detail here, looks like noise, right? Well, and then maybe here, you see some events that really, yeah, there's an acoustic emission there, obvious one that has a clear signal. Well, it turns out when you look in here with machine learning, it sees a pattern that is predictive. It uses that pattern to predict the failure time in a supervised sense. So you train the algorithm to know when the failure events are going to occur based on things it's seen in the acoustic emissions. And then it turns out you can predict for the whole range of things. This is our data. This is a prediction of the data with the data, under it. You see, it's not at all perfect, but it's very good. And in fact, okay, skipping past this, here's what's interesting about it in detail. If you look at a section right here, you can see that what this experiment had, and we thought this was a useful thing to try because we'd already gotten to the point where we could predict repetitive events. But these are events where it's kind of in this period doubling mode. It's a little bit more complicated than that even, but there's a small event followed by a bigger event, small event followed by a bigger event. So these are fast and slow events, all in the same experiment. If you train on that part of the data, you can predict not only the failure time, but also the end of failure. So you can predict the duration of failure based on the acoustic emissions that are happening in the thing. And this, I think, is the sort of last slide I want to show you about it. This is the time to failure versus some sort of measured time to failure versus the predicted time to failure for some fast and slow events. Not at all perfect, but basically, along the right line, indicates that there's something going on here that's interesting. And for me, in this talk, the main point I guess I want to make is simply that there's no scaling break that we see that indicates that, oh yeah, these events are really completely different than these events, slow versus intermediate speed or fast. They can all be explained by one thing. Okay, now I want to spend another minute acknowledging some people, Claudia and Bertrand. Especially like the fact, this was the best picture I could get of Claudia. She's trying to hide. There she is. She's fabulous at this stuff. John Lehman, who was an amazing experimentalist. Marco as well, related to that stuff, and he's in the lab in Rome. And then a couple things to say in summary, starting with this, because, okay, I actually didn't even talk too much about any of our materials, but this is true. We have done this now for gypsum and hydrite, calcite, bare surfaces of westerly granite, and quartz powder, but all under room temperature conditions, sometimes with fluids, sometimes not, under super simplified conditions, okay? So that's true. Now, what I think about that is this, but we could discuss it. You know, I suppose what I think is that when we looked at what we appreciated about Brace and Byerly was simply the mechanism, not the details, not that we thought that that westerly granite described all things, but simply that that mechanism might be useful. And so that's kind of the way I think. Quickly to summarize, part of the spectrum of behaviors from fast to slow, we can see the whole thing now in the lab. And again, not that no one had seen anything before we started doing this, but I don't know of a paper where you can easily see the whole range of things under one set of conditions. Okay, and then some things about stress drop. I didn't talk too much about this stuff, but it's useful to spend a minute. I showed you in detail this, that there's a rate dependence of K sub C, this rheologic weakening rate, that's very clear, and that can explain our data. These are quasi-dynamic instabilities in the sense that I talked about at the very beginning. And these two observations are consistent with this. Now, in Jay Feinberg's lab, using some different kind of materials, they've proven this. I have not measured the fracture energy or the energy release rate, but they have, and in any case, a description like this is consistent with what I'm showing you. When the energy release rate is just equal to the fracture energy, there's nothing left to accelerate the thing, and it just goes slow. And when the energy release rate is big compared to the fracture energy, you can make a fast rupture occur. And these other things are true, and I thank you very much for your attention.